Welcome to today's lesson, the final lesson in the transformations unit. So today we're going to write equations based on graphs. So our goal by the end of this lesson is to be able to identify the parent function of a graph, to describe the operations that have been performed on the parent function, and then finally, based on the description and the parent function, write the equation for that graph. Okay, so now, starting with this first one, all we're going to look at initially is translations, left, right, up, down movements, and reflections. We'll save the stretches and shrinks to some of our later examples. Now, looking at this graph, the first thing that we want to do is identify the parent function. Okay, parent function in this situation is the square root of x. If we were to draw the original parent function, okay, so we can make comparisons about what has happened. Okay, the red dots are the original parent function. We've got our graph line down below. So the first thing that we notice is the starting point of that graph has moved 1, 2, 3, 4 spots to the left. Okay, so that's my first description of what's happened. And then also looking at the graph normally goes up and to the right, but this graph now goes down and to the right. So we can see that that graph has been reflected vertically, okay, or a vertical reflection. So now that we have those pieces, we can start building our equation. Okay, we know that there are 4 spots that we can fill in when building the equation. 2 on the outside, 2 on the inside. Left 4, lefts are horizontal. Horizontals go on the inside. Head shake rule tells us we don't trust what we see. So we're going to put a +4 on the inside. Vertical reflections, verticals on the outside. Reflection is attaching that -1 multiplier. So now we simplify this down, and we have our transformed equation. Now, the best part of when you're dealing with a graph and you have an equation, you can always test points to make sure that they work properly. So I'm going to work on this point here, which is x equals -3, y equals -1. I'm going to plug that into my equation to make sure it works. Okay, the opposite of -3 plus 4. -3 plus 4 is a +1. Square root of 1 is 1. And then we get a y value of a -1 after inserting that -3. Okay, so I have verified a point. If you want to be sure, you can always verify all of the points. But as long as you test a non-zero point, okay, you should be in good shape in that situation. Okay, the next graph that we have, okay, once again, wanting to identify the parent function of that graph. Okay, our parent function is y equals x squared. Okay, thinking about the original position of the graph. And we always want to start with and identify where did the 0, 0 point move to. Okay, we can see that this point has moved left 1, 2, 3, 4, 5, 6 spots. Okay, so we got 5 spots. Okay, so we have our left 5 movement. Okay, we look at the rest of the graph, nothing else has been done to it. So we can build our function. We've got the x on the inside, left movement is on the inside. Okay, we've got a +5 on the inside in that situation. Once again, you can test points to make sure that it's been drawn correctly. Okay, now, dealing with one of our more difficult parent functions. Okay, the parent in this situation is the y equals 1 over x graph, okay, or our inverse graph. Now, that graph originally, we'll switch colors here so we have different colors for the two. Okay, this graph originally starts with the butterfly pattern centered around the 0, 0 point. Okay, so the first thing that we can look at is movements. Okay, this central point of asymptotes moves up 1, 2, 3, 4, 5, 6. Okay, so we have an up 6 movement. Let's move to the right, 1, 2, 3, 4, 5. Okay, and if we look at the original pattern, okay, we've got lower left, upper right, and we can see that this has been moved. Now the hard part here is we don't know if this has been a vertical or a horizontal reflection. Okay, when in doubt, the vertical reflection is the easier operation to deal with. Okay, so we've got a vertical reflection, we've got an up 6, right 5. So now when we're building this equation, okay, this equation takes a little bit more to build. Okay, I'm just going to use f of x instead of y to get used to the different operations there. We have the value in front, and then we have our fraction. Okay, the x is inside that fraction, and then we have the value after. Okay, we know up downs are outside the parent function. We trust what we see, so we can put the plus 6 on there. We've got a right 5, which is an inside operation. Okay, we don't trust the inside, so it's a minus 5. And then we have a negative on the front for the vertical reflection. Okay, so once you identify yourself what's happening, this actually goes right back to our communications unit when we're dealing with the communications of each type. And now we have built the equation, and we can write it in simplified form without the blanks. Okay, once again, if you want, we've got a coordinate point that we can test to make sure that our equation has been written correctly. Okay, now, when we deal with stretches and shrinks, there's a little bit more involved here, but we want to look at and describe what's happening. We always want to start with that 0, 0 point. Every parent function has that point either as the center of the graph or as the asymptote lines where they connect. Okay, so when we look here, the 0, 0 is not a point in the graph, okay, but it is the center of the two wings of the butterfly. Okay, now from that center point, every graph should have an over 1, up 1 point. Okay, so if we start counting to our next perfect value, and in this situation, the next perfect points on the graph are here. So we notice based on that count, it's over 1, but it's up 2. Over 1, up 2. Okay, what that tells us is we have a vertical stretch by 2, okay, because that is the one multiplier that is changed. Okay, so we're looking at that over 1, up 1 relationship and seeing when we get to our next perfect value, which one of those has changed. If the over value has changed, it is a horizontal stretch. If the up-down distance has changed, it is a vertical stretch. Okay, so now we still go through the same steps. We're just going to work on our descriptions here. So what's our parent function for this graph? The parent function is the absolute value function, the V graph. And then when we look at our counts to go from first perfect point to second perfect point on either side, I have to go 1, 2, 3 to go up 1. Okay, so I have a vertical distance of 1, but I have a horizontal distance of 3. Okay, so the description here would be a horizontal stretch by 3. Now the hard part is we always have to remember with horizontals, we don't trust what we see. We can write this equation then in two ways. If we're doing the opposite, we know that a horizontal stretch, instead of multiplying, is dividing. Okay, so we could write the equation this way. Okay, or in dealing with it as a scale factor, okay, we would put the 1/3 in front. Okay, we can see very similar equations. Okay, we tend to write them with the scale factor in front instead of the dividing situation in that case. Okay, next graph we have here. Okay, we've got some perfect points, and if we notice, okay, those perfect points are not necessarily a 1-unit measurement. Okay, so I go horizontally 1, but now I'm only going up 1/2 to get to that perfect point. Okay, so we start by identifying the parent. Okay, the parent function is the square root of x. Our adjustment from that 1, 1 situation is a vertical adjustment. If I can write vertical correctly. So we have a vertical shrink by 1/2 is the operation. We know verticals are on the outside. Outsides, we trust what we see based on the vertical head shape. Okay, so we can build our equation for that situation. Okay, so that's today's lesson on writing equations based on a graph using our descriptions and parent functions. Good luck on today's homework.